What's up, bitches? Today we're going to learn the Brayton cycle with intercooling. This is going to be probably your most complex Brayton cycle. It starts at step 1. It goes into a compressor, comp. Then it goes into an intercooling, into your second compressor. That's why there's intercooling, comp. After your second compressor, it goes into a combustion chamber and then straight into a turbine. After your turbine, the air gets reheated into another turbine. Then it goes into a heat exchanger back into step 1. Heat exchanger back into step 1. This over here, step 2, step 3, 4, 5, 6, 7, 8. Okay, if this is a little too complex, don't worry. You don't need to know this by heart. Well, actually, you don't need to know any of this. It doesn't really matter. What does matter is the TS diagram. So I'm going to draw exactly that. There you go. S and T. Okay, so your simple Brayton cycle is going to look something like this. You're going to have this, but just with multiple steps, okay? Because you're going to have multiple compressors. Step 1 starts here. It goes into your compressor. Step 2. Then there's some cooling done. Then into another compressor. 4. Then there's the combustion happening. Goes up over here. Into your turbine. Then it gets reheated over here. Then another turbine, 8. And then it goes back to into your first compressor. This is what a simple intercooling Brayton cycle looks like, okay? If it says that, oh, you also have a regeneration, then you have to consider like these random points over here, point 9 and 10. Now I should have drawn that a little higher. And it goes somewhere like this, if it's at 100% efficiency. And you just follow the same steps as your regeneration Brayton cycle problems, okay? But for now, we're just going to focus on just normal intercooling Brayton cycles. Let me just erase these. Okay. What you have to know for this problem is that heat enters into your system over here, Q in, and over here, Q in. Heat exits your system over here, Q out, and over here, Q out. Your system produces work over here, work out, and over here. Work is being done on your system over here. W in, over here, and over here. Okay, this part over here. Keep in mind that wherever you see a straight line, straight vertical line, it means it's an isentropic reaction. That means that whenever you have these points, you have to consider that T2, T1 equals to the pressure ratio to the power of K minus 1 over K. Okay? This is what isentropic means. Okay? It just means you have to use these equations. And these parts over here, it's constant pressure wherever you see the curved line. CP, CP. Okay? That's it. For this problem, what you really need to know is this TS diagram by heart, okay? And just understand that heat enters here, where heat leaves, and where work is being done, okay? I'm going to give you... Damn, what the fuck? I'm going to give you guys the equations for work in and work out. But just keep in mind that literally you just need to know, like, if you know this, you'll be fine. Okay? Actually, I'm going to write it on the side over here. So, work in is over here and over here, right? So it's CP T4 negative T3 plus CP over here. T2 negative T1. That's it. work out is equal to Cp. Work out is over here, T5 negative T6. And over here, wherever you see the straight line, T7 negative T8, okay? These might be a little confusing because of the numbers, but if you know this TS diagram by heart, this should be like really, really easy. Q in is equal to Cp, T5 negative T4, plus Cp, T7 negative T6. Heat exits your system, to find the heat exiting your system, it's equal to T8 negative T1 plus Cp, T2 negative T3. That's it. That's all you need to understand, okay? Well, these, you don't really need to know these necessarily by heart. But just understand this TS diagram and the rest is super easy, okay? Sometimes in your question or in your problem statements, it's going to say that, oh, T1 and T3, they're not the same temperature. If that's the case, you have to find the different, like the temperature difference. But generally, if it doesn't say anything, you could consider that the T1 and T3, they're the same temperature. And T5 and 7, they're the same temperature. And 6 and 8 are the same temperature. Same thing with T2 and T4. You can consider that they're the same temperature. And the rest is super easy. I'm also going to do an example, fuck it, just so you guys understand, okay? Just give me a second. All right, so I picked out this problem. It's super easy. I'm not going to read it, but I highlighted, sorry, whatever is important, okay? So first thing you do when you have a Brayton cycle problem is you draw your TS diagram. No questions asked. Okay. Well, first of all, here we could see that it's a two-stage, okay? Like first read your questions and then you draw the TS diagram, okay? Here we have two stages of expansion, of compression and expansion, okay? So it's going to look something like this. Up here and over here. Back over here. Next, pressure ratio across each stage of the compressor and turbine is 3, okay? That's just a fancy way of saying P2 over P1 equals 3, okay? Air enters at each stage of the compressor, 300, and each stage of the turbine at 1200. Determine the backward efficiency. Okay, whatever. Step 1, 2, 3, 4, 5, 6, 7, and 8. All right. So here it's telling us that when it's telling you that the compressor operates at 300K, it basically just says over here it's 300. Okay. Since it's saying that each of the stages, it's basically saying that T3 and T1 is the same. Okay. If it's not the same, the problem statement is clearly going to say it. Okay. So just watch out for that. So we're going to write T1, T2, T3, T4, T5, 6, T7, and T8. To answer the question, I think you need all of them, but it's super easy to find, don't worry. So each stage of the compressor is 300K. So it starts at 300 and T3 is the same, 300. And then the turbine is 1200. So over here on top, it's basically saying that these two are the same, 1200K. T5 is 1200. T7, 1200. We need to find the back work ratio, which is back work ratio. It's basically equal to the work done on the system divided by the work done by the system, okay? Keep in mind that this is work out and over here too, work out. Work in is over here. Well, let me write it here. Work in is here and over here. Wherever you see a straight vertical line on your TS diagram, keep in mind that it's work being done or done by the system and that it's isentropic. It's an isentropic reaction, meaning you can use this equation. Okay. All right. So, well, this is super easy actually. So to find T2, bro, literally you just do, we're just going to use this equation. T2 equals to, we send this to the other side, T1 times P2 over P1. And K, we're considering it to be 1.4. We're considering an ideal air. 1.4 negative 1 over 1.4. So 300 times the pressure ratio, 3, 0.4 to the power of 0.4 divided by 1.4. This is going to give you a value of about 410.62 Kelvin. That's T2. Okay. Since it's not talking to you about since the question isn't talking about any of the compressor efficiency or turbine efficiency, you can assume that these are like at 100% efficiency, meaning it's going to be a straight line on your TS diagram. Since they're both operating at the same temperature and the same efficiency, whatever, you can assume that T2 and T4 is the same. 0.62. All right. And just like that, we're halfway done. Now, next to find T6 over here. Remember, it's a straight line, so you can use the isentropic formulas. T6 over T5 equals to P6 over P5. And since this is going down, unlike 1 and 2, that's going up, this is going down. It's negative 0.4 over 1.4. T6 equals to 1200 times 3, because the question says that both the compressor and turbine has a pressure ratio of 3. It was 0.4 over 1.4. This is going to give you a value of about 876. What the fuck? 876.7 Kelvin. Okay. We're also assuming over here is the same because both of these operate at the same temperature, and we're both assuming that they have 100% efficiency. So even if you do the calculation, even if you do what do you call it, T8 over T7 equals P8, blah blah blah. If you do all this shit, you're gonna get the same value. So we can just assume this is gonna be the same. All right. Now we have all of the values, and we're ready to find the back work ratio. W out, work out, is equal to these, wherever these straight lines are, okay? CP times T5 negative T6 plus CP. We're taking T5 negative T6 because T5 is higher, and I don't want to have a negative value because that's not going to make any sense. Okay. Since these are the same, the exact same lines over here, I'm just going to multiply by 2. 6 equals to 2 times 1.004 COVID 1200 negative 876.7. The work being done by the system is about 449.2 kilojoules per kilogram. Work in is equal to over here. These straight lines over here. T2 negative T1 plus CP T4 negative T3. Again, these are the exact same lines over here. So I'm just going to simplify it by multiplying it by 2. 2 times CP times T2 negative T1 equals 2 times 1.004 times T2 is 410.62 negative 300. This is going to give you a value of about 222.12. Fuck. Sorry, guys. Give me a second. 22.12 kilojoules per kilogram. All right. Now we have everything to find the back work ratio. Our back work equals to W in or W out. W in is 222.12 divided by 649.2 times 100%. Back work ratio is equal to about 34.2. That's it. Next, to find the thermal efficiency, usually I use this formula, but since we already have the work done, I'm going to use this formula, W net divided by Q in. Okay? W net is equal to work out. Damn. Whoops. Out. Negative work in. If you can't remember by heart these equations, just keep in mind that stuff like this, the W net, it has to be positive. Well, it's gonna be positive, okay? I don't think your professor is gonna ask something super complicated, okay? Let's find Q in. Wherever you see a curved line like this, that's gonna be your wherever heat enters or leaves, okay? Wherever you see these two curved lines over here. Like for example, this is Q out. That's Q out because it's curved lines. All right. Q out is equal to T8 negative T1. Sorry, CP T8 negative T1 plus CP. This curved line over here, T2 negative T3. I can't just do 2 times CP times whatever because these lines over here, they're not the same. So I can't just do times 2 like they'll work. All right. But I have the values over here. Equals to 1.004 times T8 is, let me check, 876.7. Negative T1, I think it was 300. Plus 1.004. T2 was 410.62. Negative T3, again, it's 300. Calculating all of this. Oh, wait, that's not Q in. Sorry, my bad, guys. That's Q out. Ignore that. That's Q out. Q out is equal to about 1117.13 kilojoules per kilogram. All right, and that's it. Thermal efficiency is equal to W net, which is work out. So 649.2 negative 222.12 divided by 1117.13 times 100%, giving you a value of about 382, 300, 38. God damn, bro, 38.2%. There you go, final answer. Okay, and that's it. Anyways, but the most important part is to just understand this TS diagram. Okay, wherever there's curved lines, it's constant pressure. So, and you also have your heat entering or exiting wherever you see these curved lines. Wherever you see straight lines, it's isentropic reaction. You can use these equations over here, and there's work being done or done on the system, and that's it. Sometimes you're gonna have intercooling and reheat. So if that's the case, let me just draw it over here. You have to do some shit like this. Fuck, hold on. I'm not gonna do it just because it's like, it should be pretty easy. Okay, it's just gonna be a mix of the intercooling and reheat problems. Damn. 6, 7, 8. You're gonna consider this 0.9 and this 0.10. You don't need to find T9 or T10. What you need to find, well, first of all, if this is the case, then this part over here is your Q out. And this part over here is your Q in. Okay? That's the only difference if you have intercooling plus regen. And that's it. Thank you for watching. And this is How to Pass. Subscribe. Thank you.